So in the previous video we outlined how to estimate the total sum of squares related to a regression where we had y and x values, y being the dependent variable, x being the independent variable. The values we used here are consistent with values we obtained from Introduction to Econometrics with R, and we were on chapter 4. The hyperlink is here. These are the data points. We ran the regression, we set this out in R, we estimated the sum of squared residuals, the total sum of squares, and the explained sum of squares, and their outputs appeared here in the global environment. I just want to demonstrate a little bit more transparently how we might do that in a more kind of manual approach, where we can probably observe more directly the raw data and how we obtain some of these values that ultimately we'll use to estimate the R-squared and the use to set up the Anova analysis of variance for the regression. Previously we also had set out this type of analysis using LinEst and using the data analysis menu that's available internally in Excel. LinEst being perhaps a little bit more flexible. So what we want to do is to demonstrate how do we estimate the R-squared and set out the Anova analysis. We've already estimated total sum of squares, and we obtained that from just taking the y minus the mean of y, each y subtracting away the mean of y, and then we square that in turn and we summed up. Okay, so our next step then is to explain how we obtained the explained sum of squares, and that came from estimating the difference between what we call here y hat and the mean and squaring. So again, to explain a little bit y hat is simply the estimated y or the predicted y. We saw that previously in LinEst when we estimated the intercept and the beta coefficient in this very simple single variable, independent variable regression. We obtained a model fit, and the model fit was just basically a plus beta times the explanatory variable, and that generated the line of best fit. We can do that here also using our output here. Now to note, if we were to map out the raw data, it's very simple. We just go to Insert and go to Scatter Graph, and then we can populate our graph with some detail here. But this is on the horizontal axis. On the horizontal axis we have the student-teacher ratio. On the vertical axis we have the test scores. Now if we were to introduce the line of best fit here, we would take the y hat. Y hat is basically equivalent to again taking our estimate for beta and multiplying, so A12 beta, and we multiply by the individual independent student-teacher ratio value, and then we add on the intercept, the 713. Okay, so we do that in each instance here. And there's, okay, so let's just see how that would map in to how that appears then. So let's edit this first one and just say raw data, and then we'll add the fitted model or y hat, maybe y hat. And on the x-axis, again, the same independent variables will appear, but in this instance it's not the actual y's. We're going to actually take the model fit and include those in, and then run, and we get the same graph if you like as before. We could add in a trend line here no real need, but a linear just for our purposes. Okay, so let's do that. Okay, and that appears then in our graph. Now, what we would like to do is then reconcile that with the explanation in terms of R-squared, and when estimating the R-squared, we're taking the total sum of the squared total sum of squares. That's equivalent to subtracting in each instance the average y value, 653, and subtracting that away from the actual value. So let's just map in the mean value of y. Okay, so we'll just put here equal to 653 f4 function f4, and drag that down, and we'll map that in just to observe. So select data, and add, and we'll say mean y value. Again, we'll take the same explanatory variables, that won't change, and this time the mean value, or y bar. Okay, and let's just introduce that in, and then we can also add here perhaps a trend line. There's no real need, but it's just purely for looking at or observing our data, so we'll take this one here again. Okay, so terms of our graph, then what we have, if you like, this is the explanatory, this is the y hat, the blue represents the raw data for y, the actual y observations, and then y bar, the mean level of y, is the 653. And in trying to understand the total sum of the squares, that represents, if you like, the difference between y subscript I, so the actual y, and we subtract away y bar. Y bar is the mean level of y. We do that in each instance. And then to compare that against the actual explanatory value in our model, we take each of the y hat values. So this is y hat, and we subtract away y bar, and we square those. So if you like, all the values will be made positive as a result. And then we take the ratio of the sum of these, so these differences. So if we take each of if we're talking in terms of the explained sum of the squares, basically we have in each instance, we're taking the actual, estimated y, that's the orange, and we subtract away the mean value of 653, and we square, and we do the same, and we square. Now we need to just format that, so I'll just pause for a moment. Okay, so we have again the y hat minus y bar, so y hat minus y bar, and that gives us, when we take those differences and we sum the squares, we get 668. Again, we might look here at our Anova analysis. 668 appears here. The unexplained residuals, or if you like, the SSR, the sum of the squared residuals, RSS, is the difference between the actual y's and the estimated, the actual y value and the estimated. That's the error, and we square those and sum them, and that gives us 1466, and that's what we have here. If we go into our R for a moment and take a look at the Rstudio output, and we run the Anova linear model, we find that when we run that, let's just copy that output for a moment, copy, and go back into our Excel spreadsheet. We can demonstrate relatively simply that we obtain the same results. So the you can see 668, 668, 1466 corresponds to the residual sum of squares, which is what we have here. To get the R squared then, all we need to do is to take the explained sum of squares and divide by the total sum of squares, which is relatively trivial. We can do it here. It's equal to the explained sum of squares divided by the total sum of squares, the total sum of squares, the one below, and we get a value of 31.31.8 or 31.32, and that's consistent with the R squared that we have reported so far, 31.32 from Rstudio. Okay, using that data set. Now, we could also have done it in the way I've set it up here, which is just very simply 1 minus the residual sum of squares divided by the total sum of squares. Okay, and that also yields 31.32 also, which is consistent. Okay, in addition then we need probably to say a little bit more about the Anova. Once we have estimated the explained sum of squares and the residual sum of squares, we can then go and estimate the F value. Again, comparing like against like, the F value was 227. To estimate the F value to determine the overall explanatory power of to combine the intercept and the beta coefficient, we should take the mean squares. So we take the 668 and divide it, because it has 1 degree of freedom, we divide it by 1. Why 1? Because there was only one explanatory variable. And here for the unexplained residual sum of squares, we divided by 5 because it was n minus 2. N being the 7, and we subtract away 2 to get the degrees of freedom. That gave us 293, and then the ratio of those two mean squares produced our value of 2.2799, which is consistent with what we had here from the R output. The F value that we have here is 0.1914, which means that the overall explanatory power of the regression is poor. Should be less than, we should have a p-value less than 0.05. If we go back to our output for a moment, keep in mind we had run these numbers before, so the residual sum of squares, the total sum of squares, and explained values. There also, if we examine those values here, we can see that the SSR 1466, we can verify that with before, total sum of squares 2135, and the R squared 0.3132, and the explained sum of squares 668. So those values we had obtained before. Okay, so if we come down below then, and maybe we just print off, if we report those values, so remember it, we have TSS, we had ESS, we had SSR, and we had SER, and we can take each of these and just run and get the numbers for those values, and just copy and compare against what we had in our spreadsheet. So we come down below here and paste, and we might note here that the value for SER 1712 is equal here to the 1712